Let's continue now. In the last video, we proved that degree of an element is equal to the degree of the field generated by that element, loosely speaking. And also we showed that the degree is multiplicative for field extensions. So we are going to exploit those two facts and to make some nice observations today. Okay, so let me go ahead and prove the propositions one by one. So the first one I want to say is, let K be a field extension over F. Let K over F be a field extension, and suppose that the degree of the extension is n. Then K is algebraic over F. Okay, so I don't recall if I defined what it means for a field to be algebraic over a base field. If not, I will just quickly do this when I do the proof. K is algebraic over F. If alpha is in K, then the degree of alpha over F divides n. Okay, so let me prove this proposition before we come to the other proposition later. So let me first say what is the definition of a field extension being algebraic. A field extension, it's a very simple definition. A field extension K over F is algebraic if every element of K is algebraic over F. That's all, very simple. So an algebraic extension is one where every element is algebraic. We have already defined the meaning for an element to be algebraic. So to prove K is algebraic over F, all we need to show is that every element of K is algebraic over F. Okay, so now this is very easy. So what we have is an arbitrary element in K. We are going to prove both statements of the proposition in one shot. Consider the intermediate field F alpha. So the intermediate field, the word intermediate refers to the fact that you have F alpha between K and F. So it's an intermediate field, it sits between these two. What do we know now? We are given that this is n, and suppose, so we know by hypothesis that K colon F is n. So immediately, hence by the theorem above, in the previous video, the multiplicativity of the degree, remember, K colon F alpha is less than infinity and F alpha colon F is also less than infinity. Why is this? Because if either of them is infinity, either K colon F alpha is infinity or F alpha over F is infinity, their product, remember, will be the degree of K colon F. We have shown in part of the first case of the proof of that theorem, if the K colon F alpha is infinity or F alpha over F is infinity, K colon F is also infinity. But we are given that it's a finite degree. I mean, when I say n, of course I mean that it's an integer. That means it's not infinite. That means this, let's call that A, let's call that B, and both are infinity. So those are finite. So A and B are finite things and AB is equal to n. So first of all, we already know that F alpha colon F is infinity implies alpha is algebraic over. Okay, so this is the first part, right? We are trying to show that alpha is algebraic. We started with an arbitrary element and we concluded that it is algebraic. Hence, K over F is algebraic. What is an algebraic extension I wrote here? It means every element is algebraic. I started with an arbitrary element, nothing special about alpha. Alpha is any element and I concluded that it is algebraic over F. So the extension itself is algebraic. So this is the first part. But we also have the second part, because we know that K colon F is equal to K colon F alpha times F alpha colon K. or f alpha colon f and this is n. So f alpha colon f divides n. But remember, the crucial theorem that we proved in the previous video is that this is exactly equal to degree of alpha over f, right? This is by theorem, the first theorem of the last video. By that theorem, the degree of f alpha over f is equal to degree of alpha over f. So that divides n. So this is the second statement. So we get what we want. Okay. So this says that if you have a finite extension, okay. So also let me define this formally so that we can refer to this without any confusion. A field extension k over f is called finite. Very simple, if k colon f is finite. Okay. So a field extension is finite, its degree is finite. So what we have, the theorem proposition really said, proposition says a finite extension is algebraic. What we have said, the first part of the proposition said a finite extension is algebraic. All we assumed was that it's a finite extension and we showed that it's algebraic. Moreover, we in fact have that degree of any element in the field k over capital F in fact divides the degree. But this is a useful statement to remember, and I will remind you, or actually tell you, and we'll come back to this later, converse is not true. So that is, an algebraic extension need not be finite. Algebraic extension need not be finite. So this is for later. But a finite extension is algebraic. So as an example of this, let me go quickly tell you something that we did in the previous video. So we considered the field, for example, R over Q, the field extension, and we looked at alpha in R to be root 2 plus root 3. If you looked at this element and we want to find degree of alpha over Q. So that was the question. So we observed last time that we already know that root 2 plus root 3 satisfies. Okay, so I am going to recall, the polynomial, so let me look that up. So x power 4 minus 10x squared plus 1, or rather I will write it like this, is a root of this polynomial in Qx, right? So it's a root of this, that we have shown by, if you check that video, you will see that we wrote alpha is equal to root 2 plus root 3, then wrote alpha minus root 2 is equal to root 3 and squared, and then we did another squaring later on to get this. So that means now I am going to consider this extension. Forget R, my goal is to consider this extension. Of course, this is in R, but I am mainly interested in this extension. To find degree of this, all we need to find is the degree of the field extension. We typically write round bracket alpha, though we can also write square bracket alpha here. Degree of alpha over Q is this. This we know. What we can definitely say is that this is less than or equal to 4, and we also said this is at least 2. So this we know, right? So what I now want to do is to determine whether it's 2, 3 or 4. So let's look at this. So first I claim that, a simple fact, root 2 and root 3 both belong to, or actually I will just say root 2 belongs to Q alpha. Of course then root 3 also belongs to it, but I don't need that. So I claim root 2 belongs to this. This is a nice argument. What we are saying is that root 2 can be written as a polynomial in root 2 plus root 3, which is not a priori clear, but we can do this. So what do we do? Since Q alpha is a field, 1 by alpha is in Q alpha. Remember, Q alpha is a field, so alpha is a non-zero element, so its inverse is there. That means 1 by root 2 plus root 3 is in Q alpha. because alpha, remember, is just root 2 plus root 3. I am just writing that as alpha for simplicity. This means I multiply both numerator and denominator by root 2 minus root 3. Okay, so what I get is root 2 minus root 3 in the numerator and root 2 plus root 3 times root 2 minus root 3 in the denominator. This belongs to Q alpha because I have not changed anything. Multiplied both the thing numerator and denominator by root 2 minus root 3. So what you get is root 2 minus root 3. But what is root 2 plus root 3 times root 2 minus root 3? That's actually minus 1. This is in Q alpha. Right? So that means root 2 minus root 3 is in Q alpha. Because that negative of root 2 minus root 3 is there means root 2 minus root 3 is there. On the other hand, root 2 plus root 3 is also in Q alpha. Root 2 minus root 3 is in Q alpha. Together these two imply their sum is in Q alpha because Q alpha is a field. Two elements are there means their sum is there. Again, using the fact that Q alpha is a field, we can divide by 2. That means root 2 is in Q alpha. Very good. So root 2 is there. So our field extension now has this shape. Q alpha, Q root 2, Q. Okay, so now let's use the multiplicativity of degrees. This we know is 2. That is easy to show because root 2 satisfies x squared minus 2, which you know is irreducible, for example by Eisenstein criterion. So now let n be the degree of the field extension Q alpha over Q. What we know is that we now know 2 divides n, because if this is b, let's say, then and this is n, we know that n is equal to 2b. So remember earlier we said n is 2 or 3 or 4 in the previous video when we talked about this. These were the 3 possibilities. We ruled out 1 and we know that it's less than or equal to 4. Now we can rule out 3, right? Because 3 is not divisible by 2. So now it's either 2 or 4. If n is equal to 2, then b is equal to 1, right? Because 2 times b is n is 2, that means b is equal to 1. But if b is equal to 1, Q alpha equal to Q root 2. Okay, this is a simple exercise for you. If you have a field extension with degree 1, you should do this. That means k is equal to f. If the degree of the field extension is 1, k is equal to f. So Q alpha is equal to Q root 2. So let me continue that here. Q alpha is equal to Q root 2. That means alpha is in Q root 2. So what we have is that this top extension is trivial. If alpha is in Q root 2, alpha, remember, is root 2 plus root 3. If root 2 plus root 3 is in Q root 2, then root 3 is in Q root 2 because it's root 2 plus root 3 minus root 2. So root 3 is in Q root 2. And this is another exercise, I will leave it for you. Show that root 3 cannot be in Q root 2. This is very easy because if it is there, I will just start the proof and leave you the details. If root 3 can be written as a plus b root 2, where a and b are, recall what is the basis of Q root 2 over Q, it is 1 and root 2, and this leads to a contradiction. Root 2 cannot be written as a linear combination of a rational number plus another rational number times root 2. So that means that n cannot be 2. So that means n can also not be 2. So n has to be 4. So Q alpha colon Q is 4. Very good. This is what I said in that video. In fact, we now can say hence x power 4 minus 10x squared plus 1 in Qx is irreducible also. We can say this. See, we have no direct way of checking that this polynomial is irreducible. But indirectly we have checked that it is irreducible. Why is that? That's a polynomial, right? Why is this irreducible? We know that Q alpha over Q has degree 4. That means 4 is the smallest degree of a polynomial that has alpha as a root. This polynomial has alpha as a root. Nothing smaller has alpha as a root. So this must be the irreducible polynomial of alpha. Right? There is no other choice. It's a monic polynomial of the smallest degree that possible for a polynomial which has alpha as a root, because this is 4, so this is irreducible. So this is nice, right? We can't directly show, because just playing with polynomials and writing factors and so on, it's very complicated to show this is irreducible. But using this field theory, we have shown that it is irreducible. So now let me do the second proposition that I want to do in this video, which is very nice statement also, and it uses the previous videos results in the previous video. So let K over F be a field extension, any field extension. Now I am going to define a subset of K and which contains F. So let L be all elements in K that are algebraic over F. All elements in K which are algebraic over F. So we have K and F are given, and I have defined L here. The statement is then L contains F, and L is in fact a field. So let me prove this. So L is a field. So in fact the picture is L is here and F is there. Okay, so the proof is first part. So as of now L is a subset only. L is a subset of F. L is a subset of K. So first part is show that L contains F. This is very easy, because if alpha is in F, then certainly alpha is algebraic over F, right? Because it satisfies, this is very easy, let me just specify it, because it satisfies, or it is a root of x minus alpha, which is a polynomial over F. So every element in a field is algebraic over itself. That's very trivial, right? So L contains F, that's fine. It's a subset of K that contains F, so it sits in between. The crucial thing is, so there are two statements I am making here. The first one is trivial, but the second one is the crucial thing. So now we show that L is a field. So it contains F is trivial. Now we show that it's a field. What do we have to show that it's a field? We have to show that we need to show if alpha and beta are in L, then various combinations that you can construct with alpha are also in L. That means alpha plus beta is in L, alpha beta is in L, and if alpha is non-zero, alpha inverse is in L, right? And minus alpha is in L, and so on. So it is already a subset of K. To be a field, it must be closed under addition, it must be closed under multiplication, it must contain inverses of any non-zero thing there, and so on. Okay, so all these are to be proved. One is certainly there because one is in F. Remember, these are all subfields, so one is already here. So one is there, that's not a problem, because F is contained in L. But if alpha and beta are there, why are all these combinations there? And this is where we use the multiplicativity of the degree. So what we have now is K is there, and so we take alpha and beta in L. We consider the field generated by F alpha beta. So when I write this, remember we already understand what is F bracket 1 element. We also understand what is F bracket 2 elements, because these are all ratios of polynomials in alpha and beta in two variables, and you plug in alpha and beta with coefficients in F. Okay, so now we have F. So of course, this whole thing is in L. That is a separate fact. But L is not yet a field, but these are fields. Now the point is, we have this is F alpha and this is F. So this is the tower that we will consider. Since alpha is in L, alpha is algebraic over, by definition, right? Alpha is algebraic over F. That means F alpha colon F is finite. So this is finite. Now beta is also in L. That means beta is algebraic over F. By definition, because L consists of algebraic elements over F. So beta is in L, that means beta is algebraic over F. Now I am going to make a very nice observation, very easy and nice observation, is that beta is actually algebraic over F alpha also. Right? So beta is algebraic over the smaller field F. That means beta satisfies a polynomial with coefficients in capital F. That means that same polynomial will be also a polynomial over F round bracket alpha. So certainly beta is algebraic over F alpha. So this is easy exercise. I actually said this in words. Please think about this and you go back to that part if you want. But if beta is algebraic over F, it satisfies a polynomial over F. That polynomial actually lives over F alpha, so it's algebraic over F alpha. That means F alpha beta colon F alpha is finite. Right? This is the same statement. Alpha is algebraic over F means F alpha colon F is finite. Beta is algebraic over F alpha means F alpha bracket beta colon F alpha is finite. But that means, and this is something also as an easy exercise, F alpha bracket beta is just F alpha beta. Okay, this is also similar to polynomial rings that we considered. Polynomial ring in one variable over a polynomial ring in one variable is just a polynomial ring in two variables. Okay, so let me not say anything about this. This can be easily checked. Write down typical elements on both sides and you will see that they are same sets. So that means F alpha beta colon F alpha is finite. So this is also finite. So F alpha beta over F alpha is finite, F alpha over F is finite. That means by the product rule for degrees, F alpha beta over F is finite, because this is just the product. So this is finite. That means by the first proposition that we did, F alpha beta is algebraic over F. Nice, right? F alpha beta colon F is finite. Every finite extension is an algebraic extension. That's what we proved in the beginning of this video. A finite extension is algebraic. So F alpha beta is algebraic over F. That means at one shot you get that all elements of this are algebraic over F. That means every element of F alpha beta is in L, right? Because in other words, F alpha beta is contained in L. So I should not have written this because I was going to show this, right? F is there, alpha and beta are there. That doesn't mean a priori that F alpha beta is in L. Now we can say that it is in L. That means alpha plus beta is there, alpha beta is there, alpha inverse is there if alpha is non-zero, right? Because F alpha beta is a field. This is a field. And if two elements are there, their sum is there, their product is there, inverses are there, everything is there. So hence L is a field. So this is a nice argument. It might seem somewhat tricky initially, but please carefully listen to this again, watch the video and make sure that you understand this. This is a very typical and a beautiful argument to prove that all algebraic elements form a subfield of K. So as an example, if you take R over Q and consider K to be all alpha in R, all real numbers which are algebraic over Q. So that will sit inside R and will contain Q is a field. So this is what we call an algebraic closure of Q. This is something I will mention later, just terminology I am giving now. It's an algebraic closure of Q. Actually in R, so I should not say that. I should also include C. So let me just take that back. So it is algebraic over, it's a field, and K is algebraic over Q. That's what I will say. It is not an algebraic closure because, for example, it doesn't contain I. I is supposed to be in the algebraic closure of Q. If you replace R by C, then you get that. So K is algebraic over Q by definition, right? Because every element of K is by definition algebraic over Q, which means K is algebraic over Q by definition. And this, maybe I will do this later, K is not a finite extension of. You might want to think about this also, because it contains root 2, root 3, root 5 and so on. So root 2, root 3, it requires a bit of a proof. All are in K and they cannot be linearly dependent. Okay, so this is for later. So this is a construction. A priori we do not know that sum of algebraic elements is algebraic and product of algebraic elements is algebraic and so on. Because if you directly try to prove it from the definition of being algebraic, that means it satisfies a polynomial, things get very, very tricky. So it's not always possible to write the polynomials which satisfy alpha plus beta or alpha beta and so on. But using this trick about finite extensions being algebraic, we get the result. So all algebraic elements form a subfield. So let me stop this video here. In this video we have looked at two important things which says that a finite extension is algebraic, and we also showed that if you take a field extension and take all algebraic elements of the bigger field over the smaller field, they form a field. Thank you.